सर लास्ट
बिस्मिल्लाहिर्रहमानिर्रहीम।
टाइम आप
क्या हुआ बताइए।
सॉरी सर, मैंने आपको डिस्टर्ब किया। मैं ये पूछना चाह रही थी कि लास्ट टाइम आपने क्लास में बोला था कि 2 एमसीक्यूज और 10 एमसीक्यूज होंगे, लेकिन अभी तो पेपर ऑनलाइन चला गया, तो 20 एमसीक्यूज ही होंगे।
हाँ जी बिल्कुल, ऑनलाइन के लिए 20 हो।
ओके सर।
बिस्मिल्लाहिर्रहमानिर्रहीम। रब्बि इश्रह ली सदरी व यस्सिर ली अमरी वहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली। Welcome back. As you know, I'm Dr. Hambacha, PhD Diagnostic Ultrasound Associate Professor. Today we'll discuss about interfaces, right? So now a question arises, what is interface? So interface mean media boundary. Whenever two media join with each other, so the joining line of the two or more than two medium is called interface. An ultrasound, we are calling this interface as reflector because sound waves are reflecting back from that interface. That's why we are calling it reflector. But how will this interface will appear and will be formed in between the mediums? So if there is acoustic impedance mismatch, if the acoustic impedance of the two medium differ from each other, then interface will be formed, media boundary will be formed. If the acoustic impedance mismatch is greater, if the difference in the acoustic impedance is greater from each other, then the interface will be stronger. If the acoustic impedance is weaker, then the interface will be weaker. So the strength of the reflector depends upon the acoustic impedance mismatch, and the strength of the reflector actually represents the brightness of the echo. If there's a great difference between the acoustic impedance of the true medium, the interface will be strong, the reflected echo will be with high amplitude, and if echo with high amplitude are received by the transducers, that reflector, that structure, that interface will appear brighter. So, the ultrasound image appear from black to black to white. So this is in gray shades, right? Anyone can tell me how many gray shades were there from black to white? I think it's too
सर
difficult.
लास्ट आपने फिजिकल लेक्चर में आपने बताया था कि बहुत मुश्किल होता है कि हम बताएं, क्योंकि नंबर बहुत थाउजेंड ऑफ नंबर होते हैं इसमें।
Uncountable.
That's right.
काउंटेबल।
Is uncountable. There are uncountable gray shades. We can't say that there are some countable numbers and you can count it and you can differentiate it. But there will be a limitation, and due to that limitation, we will be unable to differentiate between structures, between the gray shades, but they will be in fact different from each other. So there are innumerable gray shades from black to white, and the brightness of the structure depends upon the echo amplitude, and the echo amplitude depends upon the strength of the reflector, and the strength of the reflector in turn depends upon the acoustic impedance mismatch. But now the question arises, what is acoustic impedance? Because we don't know about the acoustic impedance. So the acoustic impedance is the ease with which sound wave can form in a medium. Now this is a definition which is a little bit controversial to the meaning of the impedance. If you search for the meaning of the impedance in the dictionary, so you'll find that the meaning of the impedance in the dictionary is resistance, right? This is not the ease. Then how are we defining the impedance and in terms of ease, right? So it's I can say that it's neither ease neither difficulty, but it's that's the overall characteristic of the medium, because this is a medium, right? In the medium there are a number of molecules, right? This is a medium containing a lot of molecule, right? If there is space and having no molecule, it's mean that is vacuum. But there is medium, there is space, and that space contain molecules, whatever the nature of those molecule may be, but that becomes a medium. So this is a medium containing a number of molecule, and you couple a vibrating source with that. Now with the vibration of that source will move to and fro, and the to and fro moment of the source, these molecule of the medium are coming in the vicinity of the vibrating structure, and they will be heated by the vibrating structure. Energy will be transferred to those molecule, and those molecule will now have the ability to move forward, but they will in turn hit another molecule, and their neighboring the energy is gradually transferring from one place into another place. Now, how the sound waves are forming in this medium, because the sound waves are not a particulate matter, just like X radiation to pass from the muddy body, but actually this is an energy, and the sound waves are actually forming inside the medium. They are not introduced by anything else. These sound waves are generated inside the medium. That's why sound wave can be formed in different medium differently from each other, because the molecular arrangement of different medium is different from each other. So the acoustic impedance is actually the molecular arrangement of the medium. And if we mathematically represent this acoustic impedance, then the acoustic impedance is expressed with an English letter Z. The unit of the acoustic impedance is real, and the mathematical expression or equation of the acoustic impedance is speed of sound multiplied by density, right? So both of them, density and speed of sound, both of them depends upon the uh, the medium, right? What is the cost? What is density? So density, you know that the amount, the mass per unit volume is called density. So if there are a large number of molecule in a unit volume, that will be a higher density. So that's mean that if the molecules are compactly arranged, they are near to each other, then that medium will be denser. And the speed of sound, the speed of sound totally depends upon the medium. That's why, according to speed of sound, different medium are categorized in different categories like fast medium, slow medium, and you can say average medium. But you know that the different medium have different speed of sound, and that speed of sound remain constant, and that medium, whatever the amplitude of the sound wave, the frequency. So irrespective of the frequency and amplitude of the sound wave, speed of sound remain constant in mediums. Speed of sound in air is 330 meter per second, that of soft tissue is 1540 meter per second, and that of bone is 4000 meter per second, and so on. And the speed of sound is kept constant by the ultrasound machine as 1540 meter per second, because the ultrasound machine assume that all the tissues are soft tissues. So that's why it is kept constant as 1540 meter per second. So again, we can say that speed of sound depends upon the medium. So if the speed of sound depends upon the medium, and density depends upon the medium, and the molecular arrangement, so overall, we can say that the acoustic impedance is the molecular arrangement of the medium, and the molecular arrangement of different medium are different from each other. So if the molecular arrangement is different from each other of the two medium, then there will be an interface, there will be media boundary, there will be a reflector, and sound waves will reflect from that interface. Now, if the acoustic impedance of these two medium is different from each other with a great number. We can say that there is a huge difference between the acoustic impedance of the two medium. Mean the density of the two medium is different from each other. The speed of sound in these two medium is different from each other. So if these characteristics of the two mediums are more than two mediums are different from each other, then there will appear interface or interfaces, and the sound waves will reflect from those interfaces. So if the difference or is great, then there will be a strong interface and strong echoes will reflect with high amplitude, and these high amplitude echoes will appear brighter. So now we came to the conclusion that if the acoustic impedance mismatch is greater, then there will be a huge reflection with high amplitude and that will appear brighter. So for the examination purpose or for the explanation purpose, you should know the acoustic impedance of a few medium. Just for example, acoustic impedance of the air is 0.004, the acoustic impedance of the soft tissue is 1.63, the acoustic impedance of bone is 7.8, the acoustic impedance of the crystal is 29, and the acoustic impedance of every medium is different from each other. Even the acoustic impedance of soft tissue to soft tissue is also different from each other with a little difference. For example, the acoustic impedance of one soft tissue will be 1.63, the acoustic impedance of the other soft tissue will be 1.62. So this is also difference, but this is a small difference. Due to the small difference, there will become a weak reflector, and that weak reflector will reflect weak sound waves with low amplitude, and they will appear dark on the screen. So the shade of the screen depends upon the acoustic impedance mismatch of the two medium, which makes the interface. So now if the interface, if the acoustic impedance mismatch is greater, then the reflection will be stronger with high amplitude. So how much stronger that amplitude, that reflection will be? So we can determine it mathematically with the help of a mathematical formula of IRC, intensity reflection coefficient. So now you should know that what is intensity reflection coefficient. So by intensity reflection coefficient, we mean that the uh, the percentage of sound wave that can be reflected from a reflector is called the intensity reflection coefficient, right? This is the formula of the intensity reflection coefficient. If there is a great mismatch, there is a great difference between the acoustic impedance of the two medium. For example, there are two medium. The acoustic impedance of one medium is U2, and the acoustic impedance of the other medium is U1. So U2 minus U1 divided by U2 plus U1 whole square. This is the formula of the intensity reflection coefficient. You should know about it. Actually, this is the formula which represent the difference in the acoustic impedance of the two medium and percentage. So it should be multiplied by simply by 100, and we'll get the X value in percentage, right? So if IRC is greater, and IRC will be greater if there is great difference between the Z2 and Z1. So if the numerator, the value of the numerator is greater, then the overall value of the IRC will also be greater because it's in direct relation with the IRC. And we'll get high IRC with the great difference. If the difference is greater, then greater will be the reflection. For example, this is a reflector. The sound waves which are generated by the transducer are 100%. Now, 75% of the sound waves are reflected back, so only 25% of the sound wave will be transmitted. So if 70% is reflected, 30% will be transmitted. Here you can see the intensity reflection coefficient is now 70, and the intensity transmission coefficient is now 30%, right? So the ITC, which is called intensity transmission coefficient, is equal to 100% minus IRC. And this will be the formula of ITC. 100% minus IRC is the formula of ITC, intensity transmission coefficient. So now a question arises, why are we using a caustic gel? We are using caustic gel because a strong interface is forming while placing transducer on the skin. There is a huge caustic impedance mismatch between the skin and the transducer crystal, right? You know that the acoustic impedance of the soft tissue is 1.63 and the acoustic impedance of the transducer crystal as 29. So there is a huge difference. And now you can calculate the IRC and between the soft tissue and the transducer crystal. So on one hand, FG2 is 29, right? Z2 is 29 and Z1 is 1.63. Then you can calculate the. Now a question arises that why are we using a caustic gel? So the caustic gel is used to reduce the intensity reflection coefficient and to improve the intensity transmission coefficient, right? So while coupling the transducer with the skin, we are interested in the transmission of sound wave to the body, not in the reflection of the sound wave from this very superficial reflector, which is formed in between the transducer crystal and the soft tissue. So that's why we are using caustic gel, because the caustic impedance of the gel is in between the acoustic impedance of the soft tissue and the transducer crystal. So the acoustic gel is used for that purpose. This is the technical use of the acoustic gel. For example, you are asked by any interview or anyone that why are we using caustic gel? So the caustic gel is used to reduce the acoustic impedance mismatch. It is used to improve the ITC. It is used to improve the ITC and to reduce the IRC, right? So now we were talking about the interface, right? So interfaces are formed in between the medium. When you are two or more than two medium join with each other, the joining line of the media are called interface. So this interface may be small or large. So if the interface is large enough in relation to the wavelength of the incident sound wave, then that will be a specular reflector, right? Or specular interface, as you can say, specular media boundary. So if the interface is large enough in relation to the wavelength of incident sound wave, then that is a specular interface, but or the specular reflector. But the reflection from that specular reflector is specular reflection, and that specular reflection is angle dependent. So always the angle of incidence will be equal to the angle of reflection. And if the sound waves are striking the reflector to normal incidence, for example, at 90 degree, then the sound waves will reflect back at the same degree. So here we will calculate this angle from an imaginary line. That imaginary line, reference line, will be perpendicular to our interface. So if we calculate that angle with the reference line, then we'll call this type of reflection or incidence at normal, right? At 0 degree. So this is an incidence at 0 degree. So if there is an incidence at 0 degree angle, then the angle of reflection, the angle of transmission, all the angles will remain the same at 0 degree. But if there is oblique incidence, then what will happen? In the case of oblique incidence, the angle of incidence will be equal to the angle of reflection. And here you can see all these angles are calculated with this perpendicular yellow dotted line. And this is the angle of incidence. Here you can see this is the angle of incidence and this is the angle of transmission. The angle of incidence, the angle of, sorry, the angle of reflection, and this is the angle of transmission, right? This angle of transmission. So always the angle of incidence will be equal to the angle of reflection. For example, you have placed your transducer over here. The sound waves are generated by the transducer. They are striking the reflector in this way. And now the sound waves are reflected from here in this direction. So can anyone tell me that these sound waves are coming back towards the transducer? Are you sleeping? No. Okay. So these sound waves are not coming back towards the transducer, and you see that the sound waves, the reflected sound waves, are going in another direction. They are going somewhere else. They are not coming back towards the transducer. So, irrespective of the strength of this reflector, this structure will end up here because the sound waves are not coming back towards the transducer. And this phenomena is called anisotropy, and you will face it most commonly in the musculoskeletal ultrasound, right? So you should know about this anisotropy because in the case of oblique incidence and specular reflector, because the example of specular reflector is tendon fiber, muscle fibers, and other large reflector, just for example, diaphragm, the cortical part of the bone, periosteum, muscle fascia, muscle and tendons and ligaments, fibers, and so on. That's why if the sound waves are oblique incidence to these large reflector, then they will reflect in another direction, and these sound waves will come back towards the transducer. That's why the oblique incidence, the tendon, the muscle, the ligaments, the cortical part of the bone, the diaphragm, and so on. These structure will interfere because the sound waves are not coming back from these reflectors. Okay, so this is a very important phenomenon, and you should know about this phenomenon, particularly in musculoskeletal ultrasound. You should make sure that incident sound waves are at 90 degree to the reflector, are the incidences at 0 degree. So by 0 degree, we mean that the sound waves are orthogonal or perpendicular to the reflector. Uh, There is another type of reflector which is called scatter, but the scatter will be discussed in more detail in the next class. If you have any question related to the current lecture, you can ask. I'll try my best to answer your question. So, do you